In this video, we'll find distances between points, lines, and planes using the idea of projection. As our first example, let's find the distance between the point 1, 2, 3, I'll call that point P, and the plane given by this equation. If we wanted to, we could look up a formula for distance between points and planes, but I'm going to work this problem out instead from concepts and first principles. The distance that I want is the shortest distance between P and a point on the plane. In other words, the length of a line segment from P that drops down to the plane and intersects it at a right angle. But the difficulty is I don't know which point that is that would be on the plane that would be closest to the given point. So instead what I'm going to do is I'm just going to take any point on the plane. So I'll call a point Q, and I'll just find any x, y, and z value that satisfy this plane equation. For example, the point 2, 0, 0 satisfies the plane equation. Now let me connect Q to P to get a vector QP that has components -1, 2, 3. The vector QP itself will be longer than I want, but if I project QP onto the normal vector for the plane, so I'll draw the projection here in red, then I'll just get the component of the vector QP that lies perpendicular in the perpendicular direction of the plane. That's going to be exactly the same length as this red line over here. It's going to give us the distance between the point and the plane. So the steps I'm going through were first to find any point, call it point Q, on the plane, and then to connect Q to P to get a vector QP, and then I'm going to project QP onto the normal vector N to the plane. And since I ultimately just want distance, a scalar, I can do a scalar projection. So the distance is the scalar projection of QP onto the plane's normal vector. In other words, a scalar projection of -1, 2, 3 onto the vector 5, 4, -3, since I can read the normal vector for the plane off from the coefficients of x, y, and z. Using the formula for scalar projection, this is the dot product, 5, 4, -3 dotted with -1, 2, 3, divided by the length of the vector that forms my floor, 5, 4, -3. Working out the dot product, I get -5 plus 8 minus 9 divided by the square root of 5 squared plus 4 squared plus -3 squared, and that simplifies to -6 over the square root of 50. Now you might worry that this is negative. Distance is supposed to be positive. The reason it's negative is just that my normal vector actually was on the opposite side of the plane, so a more accurate picture, the normal vector I picked out pointed that direction. And so when I do the scalar projection, remember it's assigned magnitude of the shadow. So because the vector QP and the normal vector were pointing pretty much in away from each other at an angle of more than 90 degrees, we're getting a negative answer for the scalar projection. Since I want my distance to be the positive length of the shadow rather than the signed length of the shadow, I can fix that pretty easily just by putting absolute values. So in fact, I should have had absolute values signs all the way along here. And my actual distance is +6 over the square root of 50. And that's my final answer. In our next example, we're asked to find the distance between two skew lines. Skew means that they're neither intersecting nor parallel. So one of them, say L1, might be going like this. And then L2 might be going, say, into and out of the page like this. It might be easier to imagine what's going on if I draw two parallel planes, one of which contains each line. Now we want the distance between these two lines, so that's the minimum distance between 2 points on the two lines. It's the length of a line segment that's going to meet each line at a right angle. But since we don't know what these 2 points on these two lines that are closest together are, let's just take any 2 points, one on L1 and one on L2. For example, I could let P be the point 3, 4, 1. That's the point on L1 that I get by setting the parameter t to 0. And I could let Q be the point on L2, 1, 3, 4, that I get by setting s to 0, but any 2 points are fine. The next thing I'm going to do is connect those 2 points to make the vector PQ. I can get the components of the vector PQ by subtracting coordinates of my points, so that would be -2, -1, 3. But for the length between the lines, I don't want the length of the whole vector PQ. I just want the length of the piece of that vector that points in the perpendicular direction to both L1 and L2. So if you imagine that this is a normal vector that's going to be perpendicular both to L1 and to L2, I want to project PQ onto that normal vector. So first I need to find the normal vector, a vector that's perpendicular to both L1 and L2. Well, that's not too hard. I can use cross product. The direction vector for L1 is 2, -1, 3. I can just read that off from the coefficients of t in the equation for the line. And the direction vector for L2 is going to be 4, -2, 5. So my normal vector n that's perpendicular to both those lines is going to be the cross product of d1 and d2. Let me calculate that. So I set up my matrix. My I component is going to be -1 times 5 minus -2 times 3 minus j times 2 times 5 minus 4 times 3 plus k times 2 times -2 minus 4 times -1. That simplifies to I times 1 minus j times -2 plus k times 0. So that's the vector 1, 2, 0. Now I'm ready to do the scalar projection of my PQ, just any old vector between 2 points, onto this normal vector that's perpendicular to both L1 and L2. That'll give us the perpendicular component of PQ, which will be exactly the distance between the two lines, and also the distance between the two parallel planes that contain the two lines. So let me calculate scalar projection of PQ onto n. That's the scalar projection of PQ is -2, -1, 3 onto 1, 2, 0. So using my scalar projection formula, I do the dot product. -2, -1, 3 dotted with 1, 2, 0 divided by the length of the vector that's my floor. So that's square root of 1 squared plus 2 squared plus 0 squared. That simplifies to -4 over the square root of 5. Once again, I'm getting a negative number, but that just means that in the actual configuration, the PQ is at a larger than 90 degrees angle from the normal vector that I'd chosen. If I happen to choose the normal vector in the opposite direction, I would have gotten a positive number. To find the distance, we'll just take the absolute value and get 4 over the square root of 5 as our final answer. In this video, we did a couple examples of finding distances between two objects. The objects were points, lines, and planes. The key idea seemed to be to find any 2 points, one in each of the objects, create a vector between them, and then use scalar projection to find the component of this, the length of the component of this vector that lies perpendicular to both objects.